Professor Nualart, Junior, from University of Paris 13. She will speak on upper and lower bounds for the spatially homogeneous Landau equation for Maxwellian homology.
Thank you. So let me first thank the organizers for inviting me and giving me the opportunity to speak. So this is a joint work with François Delarue from Nice and Stéphane Menotti from Paris 7. So I'm going to talk about recent Gaussian upper and lower bounds that we have obtained from this PDE with a probabilistic approach. So maybe let me first start by explaining where this PDE comes from. So this PDE called Landau equation comes from a limit of Boltzmann equation. So let me explain in a couple of words how this limit comes. So, okay, so let's start with Boltzmann equation. So Boltzmann equation, as you know, describes the movement of particles in a gas. And the solution is a function ftv, which is the density of the particles at time t and velocity v. Okay? So from physical point of view, this makes sense from n equal to 3. But from a mathematical point of view, we can study it for n bigger than 3. So we are going to assume that it is spatially homogeneous, so that f is independent of the position of the particle. Okay. Right, so that's how the equation writes. So it's a partial differential equation, and the operator q is a quadratic operator that describes the binary collisions between particles. And it writes in the following form. So it's an integral. So here, so v and v stars are the velocities of the two particles before collision. So particles are interpreted as spheres, and they have an initial velocity that I call v, and v star, okay? And v prime and v star prime are the velocities of the two particles after the collision. Okay, so the particles collide here, and then they have some velocities after the collision. Okay, so this is this part. Okay, so W is so this dW here. So W is a unit vector which is parallel to the segment joining the center of the sphere, the particles, at the instant of collision. So maybe if I want to do some, so this one, let's assume that it's here. So here the W will go more or less like here. Okay, so this has some component. Maybe let's. Okay, maybe my. Okay, right. And theta here, it's the angular formula between v minus v star and w. Okay, so therefore it goes from 0 to p1/2. Okay, so this is for those of you already know Boltzmann equation, this is a simplified version because usually here the b, this function b of theta, depends also on v minus v star power some gamma. Okay, so here I'm considering the case of Maxwellian molecules where the gamma is 0. Okay, so what does this gamma means? So well, I'm explaining this in the next. Okay, let's concentrate on this one and then I explain later. So yeah, so how does this collision work? Okay, so it's a perfect elastic collision. So the component of the velocity along this unique vector is exchanged between the two particles, while the orthogonal to omega remains the same. So this means that here, so the component which is on the same, so this is the component which is in the same direction as omega, and this is the component which is orthogonal, okay? And here is the component which is in the same direction as omega, and this is the component which is orthogonal to omega, okay? So this particle, when it collides with this one, it will take, so it will exchange the component which is in the same direction as omega, Okay, so maybe here I wanted to do something more like, I was thinking of something like that, more or less, something like that. So this one will go like this. Okay, so this component will be exchanged with this one. Okay, the same component, and the component which is orthogonal, it remains the same. And this is the new velocity, v prime. Okay, and the same thing happens here. Okay, so the component which is in the same direction is going to change with this one. Okay, and the component which is orthogonal, which is this one, it will remain the same. All right, so this will be v prime star. Okay, so this means that this is the formula for v prime, and v prime star that appear here. Okay. Right, so there's conservation of mass and momentum, so this v prime also satisfies these equalities, okay? And then, okay, the meaning of the number of collisions that we are counting is the following. So if you split the collision operator in this form, okay, so let's go again. So if you split this in this part minus the other part, okay, so what does it count? So the second part is what is called the loss term. Okay, so these are particles that that initially have velocity v, but they after collision they have another velocity v prime. So they are subtracted from the number of particles, right? But this type of if two particles, so this counts particles with velocity v that acquire a different velocity. Okay, so this is loss term. Okay, but because of this collision, it's perfectly reversible. This means that if these two particles that now acquire a new velocity v prime and v prime star, they might collision with the same angle of rotation of before, they will give rise of two particles with the same collision, with the same velocities v and v star. Okay, so that's what it says. Okay, so these are particles which had velocity v, they collide once, and then they collide again with the same angle of collision omega. Okay, so this counts this number of particles that will acquire this new velocity v. Okay, so that's the meaning of the equation, right? So let's go again. So we are considering the case of Maxwellian molecules. This means that we are assuming that if two particles at a distance r, they interact to a force which is proportional to 1 over r power 2n plus 1, which is 5 in the physical dimension 3. Okay, so this means that the general Boltzmann equation writes like this, with here the s minus 2n minus 1 divided by s minus 1. Okay, so that's the general case. So here we are assuming that s is 2n minus 1. That's why this term disappears. Okay. Okay, when gamma is positive, one talks about hard potential. When gamma is negative, soft potentials. And the study is very different from one case and another. Okay, and from a mathematical point of view, the Maxwellian molecular case is more easy to solve. Okay, so right. So what's the beta? So what's b? Sorry, b of theta is a function which is defined implicitly. It's locally bounded and has a singularity at p half. Okay, so remember that theta was the angle between v minus v prime and omega. Okay, let me recall that. Okay, so if this angle is p, so what is the angle? Yeah, so theta, sorry, was the angle between v minus v star and omega. Okay, omega is perpendicular to v minus v prime minus v prime star. Okay, so if theta is p half, this means that v equals v prime. Okay, so that the particle carries the same velocity, so there is no collision. Okay, so when the angle is near p half, one calls these as grazing collisions. It means collisions that when particles slide touching themselves, the other. Okay, so so when there are a lot of grazing collisions, the case is mathematically difficult to study, because then the formula splitting of the equation is impossible, right? Because it will take very large values. Okay, and from a physical point of view, it was observed that, for example, in the case of Coulomb potential, which means that here s equals 2 in dimension 3, then Boltzmann equation becomes inadequate because there are a lot of grazing collisions that become preponderant over all other collisions. Okay, so that's why Landau, in 1936, he derived from Boltzmann equation. So observing this, he first derived this equation from in the Coulomb case. Okay, but then one can write it in a general form. For example, in Boltzmann, in the Maxwellian case. Okay, so this is an equation on which only grazing collisions are taken into account. Okay, so I'm going to explain a little bit. So that's the equation we are studying. Okay, so here now so it's a partial differential equation, and now the operator here A is a non-negative symmetric matrix, which is a constant, that the constants depend on the particular form of the asymptotic potential that we are taking from the Boltzmann equation. And here this is the orthogonal projection matrix of B perpendicular. Okay, so in particular, AV applied to a vector V is 0. Okay, so this has a particular geometry. Okay, so the mathematical proof that the Boltzmann equation converges to Landau equation is quite difficult. Okay, and and the conversion falls in the weak sense, and this has been very much studied in the literature. Okay, so there were first papers where the conditions were very strong, papers where they were only considering some cases, but the paper that really unified all the cases and really proved the strong convergence was the paper by Villani in 98. Okay, so he proved that the weak solution of the Boltzmann equation converges to the weak solution of the Landau equation in L1. Okay. And as it was mentioned yesterday in the talk by Arnaud, there has been probabilistic proofs. Okay, so there's a probabilistic interpretation of Boltzmann equation in terms of a diffusion with jumps. Okay, that's what's done by Fournier, and where the jumps are actually the velocities. So a jump is the amplitude of the jumps are the distance v minus v prime. Okay. And this was done by Fourier, and using this probabilistic interpretation, and then Guérin gave a probabilistic interpretation of the Landau equation. Okay, and so in the Landau equation there are only grazing collisions. So this means that the particles. So we are neglecting strictly grazing collisions. Okay, this means that the particles are colliding all the time. So the probabilistic interpretation is then a continuous diffusion process. Okay, so we go from a jump process to a continuous diffusion process. That's what this limit says. Okay, and in this paper with Méléard, they show the convergence in some cases, not in all the cases, but in some cases they show the convergence of the weak solution to the weak solution of Landau equation with probabilistic methods. Okay. Right. So what is this convergence exactly? So to understand a little bit more this conversion, one need to change variables and get into spherical coordinates, and then you get this other that maybe looks more familiar, this other way of writing the other representation of Boltzmann equation. So this is only, of course, in dimension 3. Okay, and here the collision function is 1 over alpha. So here I'm in the case of Maxwellian molecules. You know, if not, the power is another. So here, so the interest is now that the singularity now is at 0. Okay, which is going to be easier for the asymptotic. Okay, so this blows up when alpha is 0, which is the case that the velocity remains unchanged of the particle. Okay, so where there is no collision, right? And then the asymptotics means to choose a potential C epsilon that converges to 0 uniformly. Okay, and that this integral converges to a finite value, which is the constant appear in the Landau equation. Okay, right. So one example, that's the example given by Villani in this paper, is to take C like that. Okay, so so with under these two assumptions, which are followed, for example, for this sequence of potentials, Villani then shows the weak solution of the Boltzmann equation weakly in L1 to the weak solution of the Landau equation. Okay, and then in the same paper he tries to explain a little bit the physical meaning of these asymptotics, which says that it's not obvious. Okay, that it remains a little bit open to choose a potential that have a real physical meaning. Okay, Because of course, if there are no collisions, that does not have effect on the Boltzmann equation, okay? So what we are doing here is you are artificially renormalizing with this function here, okay? So actually what he explains in the paper is that it's not only that we are neglecting the collision among close particles, but we are also reinforcing the mutual interaction of particles that are very far apart, okay? So that's more or less the physical meaning of these conversions, okay? But what from a probabilistic point of view, which is what I'm going to discuss now, is that we are going from a jump process to a continuous process, okay? Because the jump process that counts this amplitude of collisions. So we are now in a model where the collisions are arriving all the time, okay? They are permanently colliding the particles, okay? Right, so this was just a little introduction to explain where this equation comes from, okay? So now let's concentrate on this equation. So this is a PDE, which is called Landau equation with this matrix, okay? So I'm in the Maxwellian case. So observe that so this is the way of writing it just to see the conversion, but if now I enter the derivative inside, this can be written in this other form, which looks like a parabolic equation, right? But the diffusion matrix and the drift term, they have the solution inside, okay? So it's a nonlinear parabolic equation in the sense that the law appears, so the solution appears inside the matrix. So this matrix is very important in my talk, and it's called A bar, and B is the drift B bar. So when there's the bar, means the convolution of A with F, and B bar means the convolution of B with F. And the matrix A is this one. The vector V is known because it's the derivative of A, so it's exactly minus A minus 1 V. Okay, so it's actually like on a Sten-Uhlenbeck type operator, in a drift, in the sense that it's a linear drift. Okay, right. So let me first recall, right, and the solution is assumed to be non-negative, integral with moments up to order 2. So let me first recall the analytical results and then the probabilistic results, and then I will show you what we have done more about all this. Okay, so Villani, in another paper, he studied this Landau equation for Maxwellian molecules, and he shows the existence of a unique solution, okay, which under the initial condition to be non-negative and finite mass and energy, okay, so this means moments of order 1 and 2, and he shows that the solution is bounded and regular, okay. In the same paper, he states a lower bound for fixed T and fixed V, okay. He states this result, the existence of some constants that this lower bound holds, okay. But he gives a proof of the fact when the initial condition F is bounded below by a Maxwellian function, which means a Gaussian density, okay. So we show this fact only when F0b, the initial condition, is bounded below by a Gaussian density, okay, via maximum principle. And he says that more generally can be proved, but he didn't give the proof of the result in this paper. So a proof of this fact is given in the paper by De Villet and Villani, so 2 years later. And they do it for a slightly more general case, where gamma is between 0 and 1, and only in dimension 3, okay? And they have a condition, I didn't write it down, but they have a condition that F0b is bounded below in a ball, okay, which is not too restrictive. And they also assume a finite entropy. And again, via maximum principle, they show this lower bound by first showing that the matrix A bar is actually uniformly elliptic, using a geometry argument that I don't know if it works in dimension bigger. So this matrix A bar, so as you saw, A is completely degenerate. It can degenerate A, right? Because AB of V is already 0, okay? So this is not at all a uniformly elliptic matrix. But A bar is a uniformly elliptic matrix for any F, okay? With, of course, constants. The ellipticity constant depends on the integral of F and the integral of V square of F, which is conserved, okay? These are quantities that are conserved, right? Okay. But it's...
That means that F is not concentrated on a subspace, right?
Exactly, yeah. But it's not bounded, which is, okay? So it's not bounded with V, right? Exactly. Right, so that's what the analyst did. And what the probabilists did after that is that you write the weak solution, weak formulation of the Landau equation, so you integrate with respect to a test function, and you use the fact that the function a and v are even and odd, respectively. And you have this other formulation of the Landau equation. Again, it looks like a parabolic equation where the v star is inside the a and b. A and b are the matrices and the same matrix as before and the same vector as before. Okay, so the probabilistic interpretation was given by Guérin. So she started to say, okay, if you let's assume that I'm starting with a density function. Okay, then I will have a density all along the time. Okay, because there is conservation, and it's natural to search for a flow of probability measures that satisfy this equation. Okay, so this calls PT a solution of this equation. She calls that a measure solution of the Landau equation. Okay, and there are two ways of solving this problem. One way is to associate the martingale problem, and the other is to associate a stochastic differential equation. Okay, both are related. Okay, so let me just explain the idea. So the martingale problem will be to find a probability measure on the space of continuous function that for any test function, the following is a martingale under P. Okay, so P is the marginals of the under P. Right? So X is the canonical process such that under P has log PT. Right? So if P solves the martingale problem, then PT, the marginals, is a measure solution of the Landau equation. This is just Ito's formula. Okay, just take expectation. That's it. Okay. And if you take the quadratic variation of the martingale, then you get exactly the integral of this, okay, of the matrix, of the Landau. Okay. So, and this matrix is symmetric, so this means that there exists a matrix sigma such that sigma transpose equals A. Okay. So by the representation theorem of white noise or more general martingale measures, we know that we can enlarge the probability space and have n independent white noises with covariant measure pt dv star dt, such that the matrix has this integral stochastic integral representation in the sense of Walsh. Okay, so we can consider the stochastic differential equation driven by this space-time white noise. Okay, well, not space-time with this covariant. Sorry. Okay, and now, but Ito's formula, the law of a process that satisfies this equation, is a solution to the martingale problem, so is a measure solution to the Landau equation. Okay, but this equation is not very satisfactory because the law of the process is inside the covariant of the noise. Okay, so that's why she proposed another representation using a Skorokhov representation theorem that says that for any probability measure P, with the topology of uniform convergence, there exists a random variable y in this probability space, just 0, 1 with Lebesgue measure that has low P. Okay, so she defines the following stochastic differential equation: a couple of processes x, y in these two probability spaces is a solution to the Landau stochastic differential equation if this equation holds true, where for any t fix, the law of xt in his probability space is equal to the law of yt in his other in this other probability space. Okay, so essentially the integral between 0, 1 of y s alpha d alpha is the expectation of xt of xs. Right? So the integral between 0 and 1 of y s alpha d alpha, this is the expectation of xs. Okay, right, and then so the common flow is the solution of the Landau stochastic differential of this equation is a measure solution of the Landau equation given the initial condition. Okay, so then what she did is to solve this equation and show that there's a strong solution. Yeah.
What is n? W.
Independent.
N.
Okay.
N is the dimension.
Yeah, okay.
Mm-hmm. Yeah, so here we are in any dimension. Okay? Right, so this is a little bit, maybe a little bit strange, but it's just think about this as an auxiliary probability space that allows to write this in terms of a space-time white noise. Okay, so now the covariance is not, the law is not more on the noise, it's on the coefficient signal. Okay, So it's another way of writing things. Right, so sigma is not unique, okay, but it contains an example, a particular example, for example, in R3 is this, okay? And so in particular, one can assume that sigma is Lipschitz with linear growth and C infinite with bounded derivatives, okay? So in this paper, Guerin shows, to summarize, that given n independent white noises with space-time white noises, x0 independent of W, of finite moment over 2, there exists a unique solution which is unique in law of the Landau stochastic differential equation. Okay, so the law depends not on depends only on P0, but not on the choice of W or X. Okay, so it's a strong solution in this sense. Right? So we conclude the existence and uniqueness of a measured solution of the Landau equation. Right? And now, if you want a solution of the Landau equation, you just need to show that the law of this stochastic differential equation has a density. Okay, and we know a very known techniques to do that, which is to use Maxwellian calculus, and that's what Guerin did in her second paper. Okay, so the existence and uniqueness of the weak solution of the Landau equation, it suffices to show that the measured solution is absolutely continuous with respect to Lebesgue measure. Okay, and she did this in this other second paper. So, and for this, he needed an additional condition, which is x0 is not a Dirac mass. If x0 is a Dirac mass, there's only one velocity at the beginning, so there are no collisions. Okay, so the solution of the Landau equation is P0, which does not have a density. Okay, so in this case, there's nothing happens. Okay, so it's a natural condition. And what she showed is using Maxwellian calculus is that the regular version of the conditional distribution of xt given x0, with solution to the Landau SD, is absolutely continuous with respect to the Lebesgue measure. And this density function is of class C infinite B and bounded. Okay? So in this case, there exists a unique weak solution of the Landau equation with initial data P0, and it's given integrated with respect to the initial condition. Okay? So this is a, yeah?
But this is strange, right? I mean, you start on a submanifold, you stay on a submanifold.
Well,
Is this in the theorem?
for
I mean, sorry, in
x0, you mean?
if you where is the real dimension in the theorem somehow? If you have, I mean, you can just reduce the dimension.
Yeah. Well, if I understand, maybe if you are saying that, for example, x0 can just be like I said here, x0 can be very degenerate. Just the sum of two. So maybe you can start with two velocities.
No, I mean, if the velocities are in a subspace, then the law of the Landau equation should keep them there, right? In
It's one subspace of dimension what?
Well, any dimension
any
lower, of course.
Lower of n?
Yeah, lower than the full space.
Yeah.
And how is this covered? Well, I mean, you say there is an integral over Rn, and it should be then over the subspace, right?
Uh-huh.
In principle.
Yes. But you will see later that there are things that happen when the subspace, for example, dimension 1. But if you have at least, okay, the most degenerate case is the case that you have x0 as sum of two Dirac masses. So you start with only two vectors, v1, v2, but they are not collinear. In this case, then you have a solution of this type, and it's okay. I mean, yeah, because here you're integrating,
No,
but
I mean,
you're integrating only with respect to x0.
maybe I didn't get the Landau exchange term correctly, but it, if you are keeping,
well,
I mean, if
I'm keeping the
energy and momentum in this with this particular law, you have just a weight in front of it. Isn't it then true that you never leave the span of these?
the what?
I mean, well, I mean, you start with some v's, and you are always staying in the same kind of subspace because v minus v star is in the subspace, so you're not leaving that. how do you get this kind of so maybe there was something I did not understand about the collision operator in the Landau equations.
I don't know. Maybe we can talk about it later, because now I don't know. Well, okay. What I was saying here, which is the remark I added, is that the only case which is not included here is the case where there is a Dirac mass. But we are not saying that X0 needs to have a density. That's what I was saying. That you can start with a very degenerate case, so just two velocities, and right, that's it. Okay, let me go further, because if not, I won't have time. So, so what is the key of the key proof? So as you know, if you want to show the existence of the density with Malyaven calculus, you need to show that the Malyaven matrix is inversible. Okay, and actually this reduces to show that this matrix, which is a bar of XS, is invertible at Moucheur. Okay, so this is more or less. So this is a leap. Remember that the analysts had already showed that the matrix A bar is uniformly elliptic. Okay, but here this was done without using any preceding result. Okay, so right. So actually, Guérin showed that if X0 is not a direct mass, then the matrix is invertible. Okay, and then so she obtained the strict positivity, so the existence of the density. And if you want to show that it's differentiable, then you need to obtain moments from the inverse, which is equivalent to say that the matrix is uniformly elliptic, but not the whole matrix, just the matrix evaluated at XS. Okay, and right. So she was able to show this using this fact, because the Malyaven matrix is because X0 is not constant. Sorry. Okay. Okay. So right. So this is just a remark to say that one can think that because we have a parabolic equation, we could have a probabilistic interpretation with respect to Brownian motion instead of space-time white noise. Okay. So, but the problem is that showing strong existence and uniqueness in law, existence and uniqueness in law of this solution, it's a very difficult problem. So now what we can say, because we have the results by Guérin, is that if we write this equation with A bar square, we will have a weak solution of this equation given the Brownian motion defined in terms of xt. Okay, so this is just a remark that with Guérin results we also can have this other weak probabilistic interpretation. Okay, right. So let's go to the focus of my talk, which was so what is the idea here? Remember that the analysts had at least conjecture and more or less proved a lower bound on Gaussian type. And as you know, Malyaven calculus also allows to get lower bounds. So it will be interesting to have a probabilistic proof of the lower bound of the Landau equation, right? Right. So we started. So with Guérin and Melea, we started this problem in 2006. So now under this additional condition, which essentially is that X0 is the support of X0 is not in a line. So for example, the sum of two Dirac measures which are not collinear. Then the matrix is uniformly elliptic in XS. Okay, so this was more or less what Guérin had already suggested. Okay, and then we applied the techniques of Malyaven calculus, but it was a little bit difficult because remember that A bar, okay, is uniformly elliptic, but it's not bounded. So the classical result did not apply. So we used some ideas of Lat-Bali that studied lower bounds for diffusions which are only locally bounded or locally uniformly elliptic. Okay, so we were able to prove this lower bound, which is not Gaussian because there is this extra term here. Okay, so that's what we were able to prove at this moment using this known technique. Okay, and then we also studied a little bit the upper bound, and again with Malyaven calculus we were able to show this upper bound in terms of the tail of the diffusion. Okay, also with the integration by formula Magellan calculus. Okay, so with my new two co-authors, we started just some months ago. So I will take this. So we started this problem, and we tried to go further and try to see if we can get the Gaussian bound that we wanted. Okay, and so we consider. So let me recall the solution of the Landau equation with the initial condition. So now assume that the initial condition is fixed. Okay, and so we were able to find an upper bound for the distribution for the tail distribution, applying the iter process to the process ZT, and using the geometry of the matrix of the Landau equation. Remember that it's a projection on the orthogonal space, so this is 0. So in particular, this term is 0. Okay, because when you apply the iter formula to this process, you get a martingale. So the idea of getting upper bounds is to apply the exponential martingale inequality, but for this you need the quadratic variation of the martingale to be bounded. Okay, so which is not the case if sigma is any sigma, but using the geometry of this specific sigma, you can reduce to a bounded martingale. Okay, and applying the exponential martingale inequality, you get an upper Gaussian bound. Okay, and the constants are completely explicit and only depends on the moment up to order 4 of the initial condition. Because remember that of x of the solution. Okay, and then putting all the two results together, so we have an upper bound of Gaussian type of the solution of the Landau equation. Okay. Of course, integrating with respect to the initial value x0. Okay. So, in particular, if x0 has a density, then the law p. Actually, here, I'm missing the p0 d x0. Okay, there's a misprint. So, if you start with a density, then you just integrate with respect to this initial density. Okay, but if you start with, as I said, with a sum of two Dirac masses, then you will have a sum of two Gaussian densities. Okay, right. So now let's go to the lower bound, which is the most difficult part. Okay, so we have started to prove in a probabilistic way that the matrix A bar is uniformly elliptic. Okay, which the analysts only prove it in dimension 3. Okay, so we were able to get a result in any dimension. And because remember that with Sylvie and Guérin, we were able to prove the uniform ellipticity with XS. So now we know that the density is strictly positive, so in particular we have kind of uniformity almost everywhere, okay? But, right, so using again the geometry of the matrix, we were able to prove that. So now, so lambda is this parameter. So when lambda is less than 1, so lambda is less than 1 is the same condition that we had before, which means that x0 is not in the support of x0 is not in a line, in a space of dimension 1, then we have uniform ellipticity. But if lambda equals 1, then we have this term 1 minus exponential minus 2 and t, so when t equals 0, this is 0, right? So we have uniform ellipticity only away from 0. Right, so in intervals of the form epsilon infinity uniformly in epsilon. Okay, so in particular for a small time, these behave like t. Right. So that's the first step, and secondly, we prove the following theorem. So with the same condition on the analysis, so that the initial, so we started with the case that x0 has a density, such that is bounded below in a ball, so it's the same condition as the analysis. And we were able to prove this lower bound, which is of Gaussian type. In particular, if v goes to infinity, so if v is bigger or equal to m, you just here you just put u squared plus v squared, and you get exponential minus v squared times a constant that depends on n. Okay, so this is exactly the results from the analysis. Okay, with a probabilistic proof. Okay, But here we have a diffusion where x0 does not need to have a density. So we can say more things. We can, right? So what happens if x0 does not have a density? I mean, we already have, we still have a solution. We still have a density if x0 is not a Dirac mass. Okay, so we can also study the behavior of the density in this case, and in this point we get very interesting results. Okay, because we try to put together the two results, the result on the density and the results that I previously obtained with Guérin-Méliard. So remember that if x0 does not have a density but satisfies this condition, remember that we had this lower bound. Okay, so you can choose a point in a ball such that the probability that x0 and x0 are away in a ball of radius square of t is strictly positive. Okay, so then for v, which is in this ball, you have this lower bound. Okay, just putting this here. Okay, so the idea here is to apply our theorem to the process xt plus s minus x0 bar, where xt minus x0 bar as initial condition has a density. Okay, because xs minus x0 bar is also a solution to the Landau SDE. Okay, so it has a density. Okay, so if you apply our theorem to this process, you get this lower bound of Gaussian type. Okay. And this term, of course, will depend on how x0 is, right? So if x0, for example, has an absolutely continuous part, which is bounded below on a ball, then you can choose x0 in the center of the ball. So for t small, this will be bounded below by t over n over 2. So you will recover the same statement of the theorem, the lower bound of Gaussian type. And if x0 has a Dirac mass, then you can choose x0 to be the center of this Dirac mass. So this probability will be bounded below as t tends to 0, and then in a neighborhood of x0, we found that the densities of order t minus n over 2, which is the standard rate of non-degenerates of a Gaussian diffusion, right? Of a diffusion process, okay? And the off-diagonal is of Gaussian type, okay? So we recover also the Gaussian behavior in cases where x0 does not have a density, okay? Which is very interesting, okay? So now just couple of minutes, as this clock says.
Still 3 minutes.
3 minutes, okay. So just let me give you a sketch of the proof of our theorem. Remember that we are starting with a density which is bounded below in a ball. Okay? And remember the equation, so we are considering the equation as a stochastic flow in X. Okay? And the idea of the lower bound is to make a change of variable. Okay? So by Kurita, this is a diffeomorphism. And you can change variables, and so this is like your density can be written in terms of the integral of the initial density, and then doing the change of variables, you get the Jacobian, which is the determinant of zt evaluated at the converse of the mapping xtx, right? And now, if you use now the fact that f, the initial condition, is bounded in a ball, then you get here that just and you use Cauchy-Schwarz, you get the inverse of the expectation of the determinant of the gradient of the process times the probability that this is less than or equal to n. Okay, so now the work is to estimate these two terms. But Kunita also gives explicit equations for the converse of a stochastic flow, right? So well, first we started to write the dynamics of Zt. So for this, we choose, so I will only show the argument for n equals 3, but the argument also works for any dimension. So the idea is to choose a specific sigma, okay, such that the gradient of sigma does not depend on v, okay, so something which is linear, because then you get a dynamic which is independent of z, of little x, okay. And right, so then you just apply Ito's formula, and you get the determinant is just an exponential. Okay, so that's the idea is to choose the sigma in a way that everything is linear, and then here you get just a linear equation from which you can compute the determinant. Okay, so this is just lower bounded by an exponential. Okay, so this term was quite easy. So the most difficult part was this one but again we're working with this specific sigma. Okay. And then the idea was to write down, using the results by Kunita, the dynamics of this converse process. Okay, and for doing this, we applied the general ethos formula to see that because everything is linear here, actually the dynamics of the converse process is just this term plus a linear term on V minus expectation of xt. But because the mass is conserved, this is only in terms of expectation of x0. Okay. Right, so at the end, we can write the probability that this process is less than m to the probability of this guy to be less than exponential minus tm, okay? But this is just the expectation of x0, and this is a Gaussian process whose covariance matrix is uniformly elliptic because it's the same result as before, depends on A, and can be well bounded, okay? And we get the lower bounded that I just mentioned. Okay, so I'm just giving the references of the papers that I mentioned. Okay. Thank you for your attention.
Thank you. Questions? Please.
There's one question which I still have. When you think about just, I mean, without looking at the mathematics, just heuristically, what is happening in these collisions? You are going from this Q, this collision operator Q, to something where you locally are looking at a diffusion operator, so you are averaging the somehow for each V, you are averaging the
we already
relations with the other FOV.
Exactly.
That in order to get out an operator for each V, which is only degenerating in its own V direction, doesn't it mean already that the kind of interacting atoms, if I think about it, has to be in the orthogonal direction to V of full measure, or at least let's say that its linear span has to be of full measure. Because I mean, in the Maxwell equation, isn't it so?
Lie like this.
Well, I mean, in the Maxwell equation, I thought that the law which you had was just the reflection in the orthogonal V minus V star direction. That would mean that you are always staying in the same kind of sub.
No, because then when you collide again, the angle can change. I mean, you are.
Well, I didn't understand. I mean. So
Yeah, what I said. No. Okay, what I said. I start with these two guys.
Yeah,
I collide, and I get this Y.
You have only 2 point collision, right?
Yeah, only 2 points. But what I was saying is that if I collide again with the same angle, you are getting these. But you can collide with any angle.
No, that's
These
true.
are
But
not
I mean,
points, these are spheres. So there's a three-dimensional ingredient.
but where is that's what I did not see. So you have 2. So you take 2
Spheres.
V1 and V2, right? And where in this kind of thing, I understand that the intuition is kind of these huge spheres of the Coulomb potential, but where is the kind of the random part in the V which you get then out? That's something which I didn't see. I mean, you have two things colliding, and you are which are colliding, let's say, in a plane. And then, what did you put in as the collision operator, the distribution in the orthogonal plane? But maybe I didn't get this. Maybe if you show the Q again, I see that. The Q for the Maxwellian Q, which you put there. I think that's probably what I missed in this explanation. That's just this Q.
Sorry, I don't know how to do it quicker.
That's just at the beginning. So let's see. It's the integral over.
So you are integrating on all the possible, let's say, vectors that you can have. So all the possible
But if the two velocities are in the plane of the blackboard, the centers of the spheres are not necessarily in that plane.
Yeah, exactly.
So when they collide, they will not remain in that plane
Yeah,
either.
because when they collide, you take the, right, exactly. This vector is not exactly on the plane of V, like V star. Right.
V star. V star. So it's an arbitrary. What is it? V minus V star.
So the collision is explained here, but
Yeah, let's see what this is. V plus V star is equals V star. Okay, so that's the only condition which you have. So it's uniform with respect to the. Oh gosh. Does it mean that this is uniform with respect to the orthogonal condition? If you take V and V prime, so the distribution is uniform with respect to the other angle, to the orthogonal angle. Or what? Is that how it is?
yeah, V minus V prime has the same direction as omega.
That's omega.
Yeah.
So it's uniform of orthogonal to omega.
Okay. Are there other questions? If not, thank you again.